signal, say 5 volts, in order for a 0 to be mistaken as a logic 1. And that is the reason that digital signals are mainly free from noise. The other big advantage of digital domain processing is that digital signals do not present us with nonlinear characteristics. That is because digital signals are deterministic and there is no continuous function processing involved. Another advantage, big advantage of digital domain processing is the integrity of data transmission. Digital data can be transmitted from one place to another with high integrity. That means that data that is transported from one point to another point can be transported in such a way that accurate data transmission is achieved. That is, the data that was intended to be transmitted is actually received at the receiving end, without spurious information being included in the transmitted data. The reason this is possible is because as the data is being transmitted in a digital format, it is possible for the receiving end to actually calculate the data that was sent. And if the local calculation at the receiving end does not tally with the type of data that was sent from the data sending end, then a data retransmission can be requested. This ensures that data can be transmitted with high integrity. And that is the reason that a lot of data can be transmitted all the time with accurate fidelity across networks such as the worldwide internet. There's also a lot of data security that can be guaranteed through digital transmission. Another big advantage of digital data transmission and digital data handling is that data can be stored and retrieved quickly and efficiently through various powerful digital memory systems. And finally, data can be easily manipulated through complex mathematical algorithms if it is in the digital domain. And that means that data can be processed through various types of processors, microprocessors, microcontrollers, and digital signal processors with the use of complex mathematical routines. Digital information comes in various forms. It is usually encoded as one of a number of different number systems. And the number systems that is most commonly used for encoding digital data is the binary number system. And there are good reasons for this, which we'll soon see. Data encoded in binary numbers appear as a series of ones and zeros. These ones and zeros are called bits. Other number systems, such as octodecimal, octal, and hexadecimal number systems, are also frequently used for expressing data in digital systems. However, at the most basic level, data is processed in all digital systems purely in a binary data format. Data can be organized in different logical ways in a digital system. Apart from the zeros and ones, that is the logic low and logic high of digital information, data can be organized in 8-bit format called a byte. So 8 bits form a byte. Data can also be organized in larger formats of multiple bytes called words. So a word can stand for 1 byte, that is 8 bits, or 2 bytes, that is 16 bits, or even 4 bytes, that is 32 bits, and even more. It is usually clear from the context that whenever a word is meant, how many bytes are implied. Now, in order to actually send data or process data, while we deal with logic zeros and logic ones, that is logic lows and logic highs, for physical representation, data has to be encoded in the physical form. That is, it has to be represented as a definite voltage level. These voltage levels for binary representation, that is for representing binary 0 and binary 1, differ according to the type of protocol that is being used. For example, transistor-transistor level or TTL protocol can represent data as 0 volt and 5 volt. 0 volt standing for logic low and 5 volt standing for logic high. Actually, a voltage from 0 volt to a certain upper voltage level can stand for logic low, while a logic from 5 volt down to a certain lower voltage level will stand for logic high. Again, there are different protocols. For instance, RS-232 protocol again uses different voltage levels for expressing data. Now, sometimes data needs to be changed when it's being sent from one system to another, which may be as simple as sending data from one IC on a PCB to another IC on the same PCB. And while this data interchange is taking place, the data may be sent from a TTL type system to a CMOS type system, or vice versa. In these cases, a voltage level translation has to take place. Digital data that is sent from one digital system to another can be sent in various different ways. It can be sent across a system so that it is sent from one machine to another, or it can be sent from one subsystem on a PCB to another subsystem on the same PCB, in which case it's being sent from one chip to another chip. Or it could also be sent from one place on the planet to another place on the planet. Many different data transmission protocols are used for digital data transmissions. Sometimes data is sent serially, that is one bit at a time. At other times, it is sent in parallel fashion, that is all the bits that make up the data are sent at the same time over a set of wires called a data bus. There are positives and negatives associated with each approach, and the particular technique that is used is in the end decided by functional, operational, and performance requirements. Integrated circuits and levels of integration. Integrated circuits use transistors as the basic building blocks from which all circuitry is built. Transistors are used as switches. They can be used either as linear switching devices or as nonlinear two-point switching devices. Linear switching devices take us into the field of analog integrated circuits, whereas nonlinear two-point switching devices give us digital integrated circuits. Both bipolar transistors and field effect transistors are used for these purposes. The two-level switching of transistors is highly reliable and is the basis for all digital circuit design. In two-level switching, transistors are switched such that they are either in cutoff or in saturation. That is, they are either not conducting current or they are fully conducting current. This two-level switching is then used to represent digital zeros and digital ones. Transistors, many of them, can be fabricated together on a small piece, so-called chip of silicon, and then interconnected together in a desired circuit form to form what are called monolithic, that is one-piece integrated circuits. These integrated circuits form the basis of all types of digital systems that we see around ourselves. Using this kind of technology, all types of digital ICs, ranging from basic, simple logic gates to complex microprocessors and microcontrollers, can all be made on a single small piece of silicon. What is important to understand is that designing an electronic system to be made on a printed circuit board is very different from designing a circuit to be made as an integrated circuit. The difference lies in the fact that the design philosophy for PCB-based electronics is very dissimilar to the design methodologies used for making chip designs. So for example, when designing electronics to be made on a printed circuit board, they make use of discrete devices, that is transistors, diodes, resistors, capacitors, inductors, so on, together with integrated circuits. While designing for integrated circuit means designing mainly using transistors. Very few resistors are usually used. Design is heavily dependent on the use of transistors alone. So the two types of designs are fundamentally very different. In this course, we'll be looking at IC design that is implemented mainly using transistors. Another thing to keep note of is that making integrated circuits is a very complex fabrication process where lots and lots of transistors have to be produced on a single small piece of silicon and then connected together using metallic conducting tracks to form a desired circuit. How this is done will be discussed in another module. We have got a very large number of different types of integrated circuits available on the market today. And they have widely different levels of integration, that is, widely different complexity in terms of the numbers of transistors that have been used to make those ICs. To make things simple and straightforward to understand, we divide the levels of integration into a number of different categories. These range from small signal integration of a few transistors on a chip, for instance, from 3 or 4 to as many as 50 or 60 transistors, through to medium scale integration, large-scale integration, very large-scale integration, and ultimately ultra-large-scale integration, where integrated circuits contain upwards of 100,000 transistors. In fact, in today's ultra-large-scale integrated circuits, examples would be most modern microprocessors, there are hundreds of millions of transistors on a single piece of silicon. The various types of programmable logic devices that concern us in the first part of this course are all examples of ULSI, that's ultra-large-scale integration containing from millions to hundreds of millions of transistors. In order to make digital integrated circuits, over the years, a number of different technologies have been implemented. These range from the resistor transistor logic, that is, circuit designs made using bipolar transistors and resistors in order to make inverters and various other elements that were used in the very, very early days of digital integrated circuit production, through digital transistor logic that used diodes and bipolar transistors, to the very successful transistor-transistor logic that is still widely used. Later on, another type of technology called a merged transistor logic technology was developed by Philips and was used in many devices such as digital watches. Yet another type of bipolar transistor-based technology is called ECL, emitter-coupled logic. The main advantage of this type of logic is its very high speed of operation. And for this reason, it's used in very high-speed processors, often used for supercomputers. Later on, field effect transistor-based IC technologies were developed. At first, these were based on N-channel field effect transistors and was called the NMOS technology. But later on, a much more advanced variant of that called CMOS, standing for complementary metal oxide semiconductor technology, was developed. CMOS is outstanding for its low power consumption. How this comes about and how CMOS is used to make logic circuits will be covered in later modules. Yet another technology that's related to CMOS is called bipolar CMOS or BiCMOS, which is often used for high power applications. Many different types of digital ICs are available on the market these days. Such a variety is expected because there are many different types of digital functions that need to be performed. So, some of the examples of digital ICs that you can buy from a number of different digital IC manufacturers would include anything ranging from simple few gate ICs to various types of combinational logic circuits, that's encoders, decoders, multiplexers, demultiplexers, and so on, to latches, flip-flops, that's different types of sequential circuits. There are also more complicated ICs, of course. For example, communication chips, data translators, memory buffers, and so on. And then there are processors of many different types. The fixed function digital ICs are developed by small or large team of engineers at digital IC manufacturers. These are designed and fabricated for use in very well-defined applications. For instance, use in various types of mobile devices. The universe of digital integrated circuits, digital ICs, is so large that there are all types of integrated circuits available, from custom chips to programmable logic devices. Custom chips are great if you want to design for a very well-defined application. But what if you want to design something that you have come up with, a new circuit idea, or you are making a commercial products to be sold in small numbers, that's from a few dozens to a few hundreds? Or what if you need a functionality that is not available in any commercial digital IC? Or if it's not available in a particular form that you need it, for instance, in terms of communication protocol or speed of operation. Also, what if you need to verify a new type of digital circuit idea? It may be for research and development purposes, or it may be for manufacturing a new commercial device. For all these requirements, there are programmable logic chips available that can be programmed to perform a desired logic function. It could be a very simple function like making an adder circuit, or it could be something quite complex. In fact, so complex that you can implement an entire processor of your own design onto one of these programmable logic devices. The design of a digital integrated circuit is different depending on whether a full custom device, a full custom commercial device is being designed, or a programmable logic design is being implemented. A full custom design is done using different techniques that employ transistor level circuit design, while programmable logic design is performed using higher level computer languages specifically used for designing circuits. VHDL is the most prominent example of such a digital circuit design language. VHDL is used widely for designing circuits for programmable logic devices, but they are now also increasingly used for verifying designs for custom-made chips. The idea is that a particular design, which will be eventually implemented in a custom designed chip, can be tested through programmable logic techniques, and then if found to be correct and working satisfactorily, it can be implemented and on the transistor level for a custom design.